Hi, I am Kinsukacharyya from Physical Research Laboratory, India. Today I will talk about water formation in the star-forming regions of low metallicity galaxies. That is the galaxies which are having low metal abundance. That is, in this case, low abundance of oxygen. Water is probably the most important molecule due to its role in the formation of life. It is observed in diverse astronomical environments, starting from diffuse interstellar medium, which is low density, having a temperature around 15 to 20 Kelvin, and it is also penetrated by stellar UV radiation. Despite we found water in these regions, water is very much presence in dense clouds. It is actually in the much in higher abundance compared to the diffuse clouds. So they are efficiently found in the dense clouds. So they are also found in the protoplanetary disks and are also found in the atmosphere of the exoplanets. They are widespread in the solar system objects, starting from comets, meteorites, and of course, planets of solar system. They are also observed in the early universe. So these are the this is the oldest evidence of water found in a 12.6 billion year old galaxy. So now let us see the ways in which water can be formed. So water is very efficiently formed in the gas phase. At low temperature, it is produced primarily via ion molecule reactions. So atomic oxygen can react with H plus or H3 plus to form either O plus or OH plus, which can successively react with molecular hydrogen to form H2O plus and then H3O plus, which can recombine with electron to form water. So atomic oxygen can also directly react with H2 to form OH, but which have barriers, so it will possible only at high temperature. Then OH of course also can react with H2 to form H2. This reaction also have a barrier. So both of these steps is possible only at high temperature due to presence of activation, reaction activation barrier. Water is also efficiently formed on the surface of the dust grains. So on the surface of the dust grains, uh, oxygen can be hydrogenated to form OH, and of course OH can form in variety of different ways. So like oxygen, surface oxygen can react with another surface oxygen to form O2. This O2 can either react with another oxygen to form O3, or it can also react with H to form HO2. If it forms O3 or ozone, it can react with another hydrogen to form OH, and it can also the HO2 can also react with the H to form H2O2 and then subsequently OH. Then of course OH can be hydrogenated to form H2O. So it is clear that all the processes will be dependent, these rates will dependent on the physical conditions. Thus, the physical conditions will have large impact in the formation of water. So addition to the physical conditions, the water formation will also be dependent on the metallicity, or in this case, presence of atomic oxygen. So generally metallicity is defined with respect to the solar values. So it is a measure of presence of heavier elements like oxygen, carbon, nitrogen, etc. So for water production, so if we see that the atomic oxygen is the presence of atomic, the abundance of atomic oxygen is different in different star forming regions, so that means it will impact the water formation, and it is indeed found a large variation between star forming regions of different galaxies. So different galaxies have different elemental abundance of oxygen. So as a result, we would expect the water abundance to be different. So to understand this dependency, we have studied water formation in the LMC and SMC clouds. So they are rich in gas and dust, and they're also undergoing star formation. So there are also the nearby objects. So LMC is only 50 kiloparsec and SMC is 60 kiloparsec away. So they can serve as a basic template to study water formation for other poorly observed low metallicity galaxies, such as those at the red shift. So these are the galaxies which is far away, so we cannot study them properly. So LMC and SMC can serve as a basic template. So now the LMC is metal poor by a factor of 2, whereas SMC is metal poor by a factor of 5. So now when we study any the formation of molecules in a star forming regions, usually with low metal abundances. These are the abundances, it is somewhat reduced with respect to those are found in the very diffuse interstellar medium. So for LMC SMC, so those values were not present. So what we do, we first, for any species, we have first found out its ratios with respect to the solar value. So this value is the solar value, and so we found the ratio with respect to the solar value. So for example, say let us consider oxygen. So solar value is around 4.19 minus 4, whereas LMC value is 2.2 minus 4. So ratio comes is around 2.22. So to find the low metal abundance for LMC, we have divided this low metal abundance for solar values by a factor of 2.2 to arrive the low metal abundance for LMC. Similarly, same prescription is used for SMC. Usually in our networks, we'll have all sorts of elements. So we have followed the same prescription for all the elements. So in addition to this elemental thing, so another important aspect is the presence of dust, or the amount of dust that is present in the star-forming regions of LMC and SMC. So since, as we will see in the result section, the water is very efficiently formed on the surface of the dust grain, so presence or amount of dust grains will also have some impact in the water abundance. So for LMC, so there are in the dense clouds, this is varied between 150 to 200. So we have adopted a average value of 175. And for SMC, we have adopted a value of 520. So these values are arrived at from the various available literature. So now let us see the water abundance. So in this case, first I will present the ice abundance, the abundance of water ice, and for isothermal clouds. So in this case, the density, gas temperature, and visual extension is kept constant. However, when we searched for various the dust temperature in the star forming regions and LMC and SMC, we found that there is a reasonably large variation. So what we did, since the dust temperature will have significant impact on the grain surface chemistry, we have used dust temperature as a parameter. So we have valued the dust temperature for isothermal models from 10 to 50 Kelvin. So now this is the variation of water abundance as a function of temperature for galactic, LMC, and SMC star forming regions. So what you can see is that the water abundance is water is very efficiently formed, and typically if you take these ratios with respect to blue to red and then blue to this magenta color, you will arrive at a ratio which is pretty much close to the elemental abundance ratio of oxygen. So there is no surprise here. But one important aspect is that if you increase the temperature, so what you can see is that so by 20 Kelvin or 24 Kelvin, you can see that the water production is at least a factor of 2 down. So if you start increase further this temperature, so first of all, the peak values will move towards the higher and higher time. So that means you need more and more time to produce similar amount of water. And then of course, when you increase the temperature further, so this goes down significantly. So it is primarily because both the hydrogen and oxygen cannot stay at the surface of the dust grains at high temperature. So whatever water abundance we are looking at in these high temperatures, that is due to the freeze out. That is the water which are produced on the gas phase that will freeze out on the surface of the dust grain due to sticking. So that is what we are seeing. So at say around 50, even it's a higher temperatures, we cannot produce efficiently water at the surface of the dust grains. Whereas if you look at the gas phase abundances, so and if we change the temperature, say 10 from 10 Kelvin to 50 Kelvin, we don't see a big difference. So peak values for both the LMC, SMC, and Milky Way remain same. So gas phase has not much of a difference. But here you can see one thing is that the in SMC you can see these LMC values are actually rather a little bit larger than the LMC values, galactic values. It's primarily because the galactic surface regions are much more dust. So some of the water will stick on the surface of the dust grain. Okay, so now let us see the compare these values with the galactic values. So if we compare the water abundance of the galactic star forming regions and LMC star forming regions, in this panel we have shown compared for LMC, we will find this ratio varies between 0.2 to 0.5, that is factor of 2 to factor of 5 less. So, and we found that this will be definitely dependent on the physical conditions. So if the temperature is low, so basically we can if the typical water abundance come between 3 to 8 and 1/5, and this ratio, if you take the ratio, it is almost for all the time, starting from the early to late time, this ratio can be reproduced. But if you increase the grain temperature to higher values, so these are the actually there are indications that the grain temperature can be higher in the LMC and SMC from regions. In that case, we to reproduce this ratio, we have to we need to have larger time. Whereas another important factor that I like to mention here is the CO2 by water ratio. So it is found to vary between 0.33 to 0.47, which is actually large compared to our galactic values. So this can be only produced at the higher temperature, so that is above 20 Kelvin or so. So similarly, this is the water and CO2 by water ratio for SMC clouds. So you can see that once again, we can for the ratio with respect to galactic values can be reproduced, but for CO2 to H2 ratio here, we'll see that these values vary from low to high values, and this can only value around vary explained reasonably well when the grain temperature is around 20 Kelvin or so. So now we also have studied water formation in the warm-up model. So here you can see that the at this phase the gas and dust temperature is kept 10 Kelvin, and the density and visual extinction is evolved. So what you can see is that so the water is very efficiently formed on the surface of the dust grains. So here you can see, as I was telling, that at the latter time it will start to freeze out on the surface of the dust grain. So now if we start increasing the gas and dust temperature, so what we will see that we have increased this temperature to up to 200 Kelvin. So we'll see that this ice abundance will be fairly constant up to say about 100 Kelvin or so. And after that it will come out of the grain surface, and we'll see that the entire abundance in the gas phase. So this is the final abundance. So similarly, if we just compare the LMC and SMC value for warm-up model, so we can see that the ratio is close to the elemental ratio of the oxygen. So now if you increase the temperature, so up to around say 20 Kelvin, there is not much of a difference, but after that it starts to go down. So by 25 Kelvin, it is lower by a factor of 2 or even more. So this is once again we found the same trend that if we have initial higher dust temperature, the water production goes down. So now finally I will conclude. So what we have seen is that despite the metal pore and the dust pore, the LMC and SMC show large water production, and dust temperature plays a very crucial role, and the water production is very robust. So large amount of water is produced both in the isothermal and hot core models. So we could also reproduce observed water abundance in both the LMC and SMC. So for LMC, we found that the peak water abundance is lower by a factor of 3 to 4 compared to the galactic values, and for SMC, it is lower by a 1 order of magnitude. We can also reproduce higher CO2 to H2O ratio in LMC, which is probably due to the higher dust temperature. So I will stop here, and thank you. and now I will take questions.